All right, sorry about that. I'm back working on 2018 FRQs. We're working on FRQ number 5. We already did part A and part B. So we're getting ready to start part C. So start part C, it says find the absolute minimum value of F. Well, anytime we are finding an absolute extrema, you could use the closed interval test. The closed interval test. I guarantee you this is going to be on your AP exam somewhere. And in fact, if I go back about 15 years on FRQs, every single FRQ in the last 15 years has had this at least once. And in fact, in the 2019 FRQ test, which is the most recent one we have in this form, it showed up 3 times. Students used the closed interval test, or sometimes people call it the candidates test, 3 different times. So, in case you need a reminder of what this is, when you're using the closed interval test, you will be testing the endpoints and the critical values. You need to be considering as candidates for absolute extrema the endpoints and any critical values of the function they're talking about, which in this case is f. So, the endpoints of the interval, the closed interval that they're looking at are 0 and 2 pi. And I need to also figure out where the critical values are. Well, you might remember critical values are where the first derivative is equal to 0. We already calculated the first derivative in B. I'm just going to rewrite it. So I like to put the positive term first, and I prefer having e to the x in front of cosine. So I'm going to rewrite it like this. And then I'm going to solve this by factoring. So I'll factor out that common factor of e to the x. And then I want to see where each of these factors would have a solution. So where does e to the x equal 0? Well, it doesn't. It doesn't ever equal 0. Here's the graph of e to the x. It never actually crosses that x-axis to give you a height of 0. There's a horizontal asymptote at a height of 0. So there is no solution for that part. And I want the cosine of x to equal minus the sine of x to equal 0. Or in other words, I want the cosine of x to equal the sine of x. Well, that will happen at pi over 4 and 5 pi over 4. At pi over 4, the sine and the cosine are both root 2 over 2. And at 5 pi over 4, the sine and the cosine are both negative root 2 over 2. So they are identical. And we're limited to 0 to 2 pi, so I'm not going to continue traveling around my unit circle more than once. You might ask, well, what am I testing it in? Well, whatever I'm finding the absolute extrema of. I want the absolute minimum value of f. Of e to the x times cosine of x. That's what I'm testing. So I'm going to take each of these x values and substitute them in and see what I would get. Oh, wait a minute. I think I actually already did this. Earlier, I already did f of 0 and got 1. I could do it again if I wanted to, or I could pull that answer. E to the 2 pi would be, or when I substitute in 2 pi, I'd have e to the 2 pi times the cosine of 2 pi, which is e to the 2 pi times 1. You might be like, well, what is that? Well, pi is like 3-ish. So this is like a power of 6. E is a little less than 3. So this is like 3 to the power of 6. Huge number. Remember, we're looking for the smallest. Yeah, that's not going to be it. All right, if I try this one, this would be e to the power of pi over 4 times the cosine of pi over 4. Ew, I don't know. Like, what is this, right? So pi over 4, well, that's like 3 over 4 3/4. So like almost 3 to almost a power of 1. Times cosine of pi over 4. Well, cosine of pi over 4 is root 2 over 2. It's like, I don't know. What I do know is it's positive. I'm hoping that maybe I have one that's a 0 or negative, because that's hard for me to figure out if that's bigger or less than 1. I'm not as familiar with those numbers. So let's take a look at the next one. I have e to the negative 5 pi over 4. That makes it 1 over e to the 5 pi over 4. That's 1 over like 3 to the power of like 15 over 4. So that's a small fraction. Times the cosine of negative 5. Oh, I don't know why I put a negative here. Of 5 pi over 4. This is not a negative. What am I doing? E to the positive 5 pi over 4. Okay, so that's a big number. Times the cosine of 5 pi over 4. Well, e to the 5 pi over 4. Oh, this is a negative. I'm very happy about that because the fact that there's a negative here makes this going, this is the only one that's negative. That will have to be the absolute max. Let's see what they wanted. They want the absolute, or absolute minimum, pardon me. They want the absolute minimum value. That word value means Y value, or the output. Writing is hard today. So my final answer here is that the absolute min value is going to be e to the 5 pi over 4 times negative root 2 over 2. Now, could you simplify that more? Probably. Does it matter? No, I wouldn't spend your time on it. We do have one more part, even though I wrote that at the bottom. We're going to do part C. Let g be a differentiable function such that g of pi over 2 is equal to 0. The graph of g, the derivative of g, is shown below. Find the limit as x approaches pi over 2 of f of x over g of x, or state that it does not exist. Justify your answer. Well, the fact that g of pi over 2 is 0 means I'm going to have a 0 on this denominator when I use substitution. That makes me wonder if perhaps I will be using L'Hopital's rule. If you're going to be using L'Hopital's rule, you will want to find the derivatives of the numerator, the limits of the numerator and the denominator separately. This is the best way to write it. The limit as x approaches pi over 2 of f of x would be, remember f of x is e to the x cosine of x, would be e to the pi over 2 times cosine of pi over 2, and since cosine of pi over 2 is 0, this would be 0. So I'm going to have a 0 on the numerator. The limit as x approaches pi over 2 of g of x, they told us, is 0. So this means I'm going to have a 0 over 0. I'm being very careful to never put an equals here. This is an indeterminate form. And I'm going to use L'Hopital's rule. Now, as I do L'Hopital's rule, I know that this function f is continuous and differentiable. I can see that. I'm going to need to take a derivative in order to use L'Hopital's rule. It's also very important here that I mention that g is differentiable as well. Now, not only is it differentiable, I also can tell it's continuous. And in fact, in general, when they give me this, I often state it. I often say g is differentiable and thus continuous, kind of as a way to protect myself in case the reader thinks I needed to state that. If they state it, I almost always do as well. All right, L'Hopital's rule, you might remember, you still need the limit notation. That is absolutely required. And then we're going to take the derivative of f and put that on the numerator. We did that in part B. I'm going to rewrite it a little bit in a form that I prefer, but it doesn't technically matter. And then I'm also going to take the limit, or the derivative of g. So this needs to be g prime of x right here. Well, here's the graph of g prime of x. So I'm going to now evaluate this all at pi over 2. So on the numerator, I would have e to the pi over 2 times the cosine of pi over 2. That's going to 0 out. Minus e to the pi over 2 times the sine of pi over 2. And on the denominator, I want g prime of pi over 2. G prime is this graph. G prime of pi over 2 is 2. And so, remember, cosine of pi over 2 is 0, so this whole part zeroes out. So what I end up with is negative e to the pi over 2 times 1, which is the sine of pi over 2 divided by 2. All right, we're going to just check with the scoring guideline real quickly to see how we did. All right, so the average rate of change. Some things for you to know about the average rate of change. They must have what's called a difference quotient. You could show it with the function notation. You've got to have the minus on both the numerator and the denominator and that fraction bar. You can also show that with numbers. But, and if you simplify it, you don't have to show that difference quotient anymore. But if you started right here, you'd have to have the minus 0. And at least initially, you must show that difference quotient. And that's 1 point. We got that. All right, the next point, we did get that answer. I do want to check f prime of x. We had an equivalent form of that. And then we evaluated it with the slope, depending on kind of your process here. But this is our final answer. And so we got that. You do need to simplify this. You've got to evaluate that function. All right, part C. This was the closed interval test. Notice they want to make sure you are knowing that you've got to set f prime of x equal to 0. Go back and we check the notation that we wrote down. You can see that that's written here. Okay, it's also could be seen on the right side of this because we know that that's f prime because that was shown above to be f prime. So f prime of x equals 0, we got that point. We did identify these candidates. They wanted to make sure that you got those critical values and not just the endpoint. And then the final answer, which is what we got, just we wrote it maybe in a slightly different form because mine was rationalized and theirs was not, but that is equivalent, so that's plus 3 over 3. By the way, it's often hard to get the last one because in order to get this, you must have all of this. When they say with justification, this is the justification. So if you don't have all of the candidates, they give you 1 point for the candidates that are critical values, but if you didn't have those endpoints as candidates, you would not get that last point even if you had the right answer. You must have the correct justification of looking at both the endpoints and the critical values. All right, D, notice we did say that differentiable in continuity. And we did show that that limit of f is equal to 0, okay? And that the limit of g is equal to 0. So we got that first point. You had to do all of those things, all right? And then we applied L'Hopital's rule. So we took the limits separately. Now, when you apply L'Hopital's rule, here's what is something that's true. You must have that limit notation. And you must show a derivative in terms of x. You cannot substitute in right yet. Don't substitute in until after you've done the derivative. That'll get you this point. Then you can get to your final answer for the last point. Notice if you don't have the limit notation right here, the most you can get is the first point. Even if you have the right answer, you must have that limit written for L'Hopital's rule. All right, on to FRQ number 6. FRQ number 6. We have a differential equation. I have not seen them skip differential equations in the last like 8 or 9 years. They've always had a separation of variables with differential equations the last, I think, 7 or 8, maybe even 9 years, something like that. All right, this particular one, we're given a slope field. We want to sketch the solution curve. So they already made the slope field. We want to sketch the solution that passes through the point 0, 2. We must make sure it passes through 0, 2. We're just going to do dot to dot. There's that solution. That's interesting. But that's it. That's the solution. If you just do like the dot to dot here, follow the pattern of the slopes. Those are just horizontal slopes. And sketch a solution curve that passes through 0, 1. Oh, I'm sorry. 1, 0. Let's do the right point. 1, 0. Well, I'm just going to follow the slopes. It's like a dot to dot. Notice those tails. Students often mess up on those tails. Be careful. It's common for students to do something like that. That would not earn that point. Notice what's happening here with those slopes. They're starting to turn. So you need to follow the pattern of the slopes. All right, let's look at part B. B, let y equals f of x be the particular solution. Stop. That doesn't mean that you're doing separation of variables. Read the problem carefully. All right, keep going. Where we know the initial condition is f of 1 is equal to 0. Write the equation for the tangent line and then use it to approximate f of 0.7. This is not separation of variables. This is tangent line. Well, what do you need for a tangent line? You need a point, which they gave us. F of 1 is equal to 0. And we need a slope. Well, you don't have an equation for x or for f, but you have an equation for the slope. We want to take this slope and we want to evaluate it at the point 1, 0. So the slope we're going to be using is 1/3 times 1 times 0 minus negative 2 quantity squared, which is 4/3. So first it said write an equation for the tangent line at x equals 1, which is, we've got all the information we need. Now I'm just going to write the equation of the line. Y is equal to the slope times x minus the x value plus k. Writing that plus 0 is optional. It's up to you. There's your tangent line. Now use it to approximate 0.7. We do not get to use a calculator. So y is equal to 4/3 times 0.7 minus 1 plus 0, which you can write or not. You can leave it like that. That's your approximation. By the way, this ends up equaling negative 2/5. If you don't believe me, if you really felt like you wanted to do this for some reason, 0.7 minus 1 is negative 0.3. If you read that decimal, that's negative 3/10. So negative 3/10, those eliminate. You get negative 4/10, which reduces to negative 2/5. I just wouldn't do it though. I would just keep it. I would not go through and finish all of that because you do not have to simplify on this exam. All right, part C. Find the particular solution to y equals f of x for the differential equation that was given. Now we're using separation of variables. Okay, so for part C, here's our original equation. And we want to separate out the variables so that we can integrate this and use the original initial condition. So I would like all of my dy and dx terms to be on numerators. So I'm going to multiply this side by dx. I'm not going to need quite that much space. I'll keep the 1/3 x over here, and I'll divide both sides by y minus 2 quantity squared. Now, right here is probably one of the most common errors that people make. As we integrate this, it is very common for students to integrate the left as a natural log. This is not natural log. The integral of 1 over x to any power of 1 is natural log. Now, you can have a multiplier there, in which case I would just pull that multiplier out and think of this as 1/3 natural log absolute value of x plus c. Wow, what's happening here? Try again. You can have something added. That's still natural. But notice for all of these, x has a power of 1. All of those, x has a power of 1 on that denominator. 1 over x to the power of 1, that is going to integrate as natural log of the absolute value of x. This, y does not have a power of 1. This is the integral of y minus 2 to the power of negative 2. You would use power rule here, and you'd want to undo chain rule. You can think about u substitution if you want. You could let u equals y minus 2, so then du is equal to dy. You might notice nothing changes, okay? You can do that if you want. This would be then, if you use power rule, you add 1 to the power, divide by that new power, and then reconvert back to y. There's no real reason to use it here because if you think about this inner function, that's derivative is 1. So you could just think of this as just following the power rule because this derivative here is 1. There's nothing here to undo with the chain rule. So I'm just going to write this as y minus 2, and I'm going to add 1 to the power and divide by that new power. Over here, I'm also going to use power rule. So this would now be x squared, and I'm going to divide by that new power. I already had a 1/3. This is now 1/6. All right, so from here, I'm going to multiply everything by the negative or divide everything by negative if you'd rather. I'll rewrite this like this. So this will be negative 1/6 x squared plus c. And I'm going to find c right here, okay? I am going to eventually need to find a way to rewrite this so that y is on the numerator, but I'll just find c right here. So I'm going to do this at the point 1, 0. The output for y is 0, so this is negative 1/2 is equal to x is 0, so that's c. So, oh no, x is not 0, x is 1. Let's try that again. Negative 1/6 times 1, there we go. So c is equal to positive 1/6 minus 1/2, or positive 1/6 minus 3/6. So c is equal to negative 2/6, which reduces to negative 1/3. Let's do it the right way, hopefully. All right, so when I rewrite this, I have to go back to right here to rewrite this, okay? That's where I substituted in, that's where I rewrite. So I'm going to rewrite this as 1 over y minus 2 equals -1, or negative x squared over 6 if you'd rather, plus c. Now I'm going to want to flip both of these sides, but I'm going to get everything on the right written as one question before I do that. So this is 1 over y minus 2 equals, let's see, I'm going to just get a common denominator here, negative x squared minus 2 over 6. And now I'm going to flip both of these over. If both sides are written as one fraction, then you can write a reciprocal for both sides. If you have more than one fraction, you should not do that. And finally, I'll add 2 to both sides. Now, could you simplify this more? Sure. Do you need to? No, you don't. By the way, you could have, oops, lost my squared. You could take this negative and move it to the top instead. So sometimes there can be a little bit of an alternative answer here, but this answer is fine the way I wrote it, okay? And I think on the scoring guideline, it might look slightly different, but it'll be equivalent. All right, let's just check the score here. All right, we have both of the correct solution curves. And so you might notice theirs might dip a little bit more down than mine did. That's okay, it's the same general shape, we're fine with it. Okay, they have to go through the indicated points. They must follow the slope lines, and they must extend all the way to the boundary. Every once in a while, what students do on these is they write it like this. Nope, they don't get it. They don't get that point. They've got to go all the way to the end. Okay? All right, so we got both of those. Next, we need the equation of the tangent line. We wrote a plus 0 at the end, but that's equivalent. And we need the approximation. Notice it was okay to not simplify. That was totally fine. So we got those points. Part C, we need to separate out the variables properly. We got to that. And then we need the antiderivatives. Now, there are 2 antiderivatives. You get 1 point for this side and 1 point for this side. If you get one of them right, they will continue reading. If you get both of those wrong, you're done with the problem. You got 1 point out of 5. If you don't separate the variables, you don't get anything. They stop reading. So make sure that at least one of those is integrated properly. From there, they solved for C at a different place than I did. Notice that their C is different than mine. Their C is 1/3. That's because they did not yet get rid of this negative. If you had solved for C at even a later date, you would have gotten a different constant. That's okay as long as it's correct with the algebra that you did from the point where you did it. But you've got to use that constant and that initial condition to get that next point. And the last one is to solve for y. Notice theirs is written just a little bit differently than mine. They took these negatives and factored it out and put it in the front of the fraction. Okay, so they can write this in a lot of different ways. Your teacher or your AP reader will know how to manipulate the equation to see equivalent forms. That is the end of the FRQ solutions for 2018.